morning, everyone. My name is Mo Al-Khalaf, and I am a postdoctoral research fellow at the University of Ottawa Heart Institute. I hope everyone is healthy and safe at this time, whatever you are. Thank you for joining us on this virtual science seminar series brought to you by the BEaTS research and radio team, all working from home now, but still continuing to bring science to the community. Some housekeeping notes. The seminar will be a 30 to 40-minute uninterrupted presentation, followed by 10 minutes of questions. Today, I'll be the seminar moderator. Please keep your microphones and camera off during the presentation. If you have any issues connecting to the audio, you can call in by phone. Please refer to the email sent to you after registration for phone numbers and meeting ID and password. For all questions, please send a private chat my way. I will ask our guest speaker all questions after the presentation is done. Include your name, title, institute, or program affiliation whenever it's possible. Seminars will be available on the BEaTS Research Radio YouTube channel soon afterwards. You can check our website or Twitter for release time. Today, I have the pleasure of moderating an exciting lecture. But first, let me just switch. There we go. I have an exciting lecture by Dr. James Armstrong. And next week, we have Dr. Andrew Lee. So register for that. To say a brief few introduction words about our speaker today, Dr. James Armstrong received his PhD in functional nanomaterials at the University of Bristol. He is an MRC UKRI Innovation Research Fellow in the Department of Materials at Imperial College London. He is an editorial board member of the Journal of Biological Methods, and just like us here at BEaTS Research, he has recently co-organized an initiative called the Virtual Seminars in Biomedical Science. His research is primarily focused on developing new biotechnologies for tissue engineering and regenerative medicine. He's published on topics such as the development of gradient casting technologies for osteochondral tissue engineering, the production of acoustic cell patterning devices for musculoskeletal tissue engineering, and the first demonstration of ultrasound-triggered enzymatic dilation. Thank you, Dr. Armstrong, for joining us today. Welcome, and please take the virtual podium.
Thank you, Mo. Okay, so you should be able to see my slides. So thank you, Mo. Thank you, Emilio, for inviting me to speak here today. And thank you to everyone who's tuning in. So my name's James Armstrong, and I'm going to talk to you about how I'm using sound waves as a method of assembling tissues and materials. So I'm predominantly a tissue engineer. So just as a bit of background, this means that I'm growing artificial tissues in the laboratory with potential uses here for modeling aspects of pathology or physiology, or to use these tissue constructs in a regenerative clinical context. So my research is really based around drawing in aspects of chemistry, engineering, and physics, and applying these different disciplines to tissue engineering. But a lot of my early work focused on biofunctionalization methods, so means of modifying proteins and cells, providing them with new functionality, which we would then use to augment tissue engineering strategies. More recently, I've been involved in the development of new biomaterials and new bioimaging strategies as a means of understanding the cell-material interface. And then a major focus of mine is on complex tissue engineering. So this is the engineering of tissues with a close to native structure and function. So this has been achieved through more conventional methods such as bioprinting, and through the use of methods which are slightly more unusual, such as the use of ultrasound manipulation. So this is the region I'm going to focus on today. So just as a bit of a background to the basic theory of sound. So sound is produced from a vibrating source. This could be a loudspeaker, or it could be a saucepan falling on the floor, or in my case, it's typically the use of piezo transducers, so materials which are vibrating in response to an electrical current. So this creates an altered distribution of pressure, where you get these regions of high pressure, these compressions, and these regions of low pressure, these rarefactions. So this pressure distribution takes the form of a wave, and it's a particular form of wave known as a longitudinal waveform. So here the particles of the medium are moving in the same direction that the wave is traveling in. So this is quite a distinction here with light, which is a transverse wave. So what people commonly do to sort of understand and picture sound wave is to transpose this pressure distribution onto a plot of pressure versus spatial coordinate. And then what you can see here is the appearance of a sine wave. So this allows, under simple conditions, to characterize the wave and to pick out the amplitude and the wavelength. So everybody is capable of producing some form of sound. So whether that's through a voice box, or through clapping your hands, or even through the motion of your breathing, you'll be producing small oscillations and small sound waves. Everybody is also capable of detecting sound. So we can detect sound through our ears, or we can also detect sound through our skin. So if you've ever stood next to a bass speaker at a nightclub, you'll feel those vibrations in your body. So this means that sound waves, and this sound region between 20 hertz and 20 kilohertz, has been used for millennia for human communication. So this is the frequencies of sound which are detectable by the human ear. So more recently, the human race has been moving towards the use of ultrasound and applying this not only in communication, but also for many aspects of physics and engineering, and also in chemistry. So of all these applications here, I want to talk today about something which is quite underexploited, and that's the use of ultrasound as a method of remote manipulation. So I'm going to go back to this sound wave. So we can see here that most sound waves, most ultrasound waves, are propagating waveforms. So we have a single source, which is this green source here, and then we have the sound wave propagating away from that source, as indicated by this arrow. What we can do is we can add a second source of sound, or we can add a reflecting surface, and if we place this in an opposing manner, in a parallel manner to that first source of sound, then what we can get under the right conditions is an ultrasound standing wave. So we still have these regions of high pressure, we still have these regions of low pressure, but they're fixed and static in space. So this is a very well controlled setup and a very useful system for remote field manipulation. So what people have been doing for many, many years is placing particles into ultrasound standing waves, and then seeing these particles respond to that field. And they respond to the field typically by moving either into the acoustic pressure nodes, to the regions of zero pressure, or they move to the acoustic pressure antinodes, so the regions of high pressure and low pressure. So this occurs because the particles in the acoustic field have acquired an acoustic potential energy, and they're experiencing an acoustic radiation force, which is driving them to either the nodes or the antinodes. And the nice thing about this is that it's completely label-free. So magnetic manipulation, for example, requires the particles to have some sort of magnetic susceptibility to the magnetic field. So often requires a labeling process. Here, all you need is your particles and your medium to have a mismatch in density and compressibility. And these conditions are almost always met. This label-free nature sparked quite a lot of interest into whether this could be used as a means of remotely manipulating cell populations. So when I first started getting interest in this, right at the end of my PhD, we There was several papers out there in which ultrasound standing waves, either using surface acoustic waves or bulk acoustic waves, were used to pattern cell populations on flat culture surfaces. Many of these approaches, like the ones I'm showing here, have an initial cell population patterned onto the surface. Those cells then adhere to the surface, and then a second patterning occurs. So the phase of the ultrasound wave is shifted, and a second population is deposited. And this generally creates a very nice uniform geometric cell co-culture platform. So this ultrasound manipulation has also been applied to the field of tissue engineering. In this paper from 2014, the authors here, they used a single pressure node as a means of accumulating stem cells. In this case, they were levitating the stem cells into a cluster, and then they took these cluster of stem cells, they carried out a cartilage tissue engineering process, and used this as a means of forming hyaline cartilage. So this is a wonderful demonstration that the ultrasound standing waves are not negatively affecting the ability of cells to produce cartilage tissue. But for me, I wanted to take this even further. So you can see in the previous slide how ultrasound waves can be used to produce fine cell microstructure. So can we do this in a tissue engineering context? So this is the overall hypothesis of whether we can use ultrasound as a method of patterning aligned cell structures to sort of capture those complex tissue engineered structures. So the primary focus for this piece of work was on skeletal muscle tissue engineering. So muscle tissue is one of the most aligned structures in our body. So if you go from the cell level to the bulk tissue level, what you see is these very elongated cell structures, which form parallel bundles, which are bundled further and further up to the bulk tissue. And then this multiple hierarchical alignment of the cells enables a very well-controlled directional actuation of the muscle. So on the right here, I'm showing you a typical cell culture setup where we can use the correct media conditions and the correct cell populations to form elongated myotubes. These muscle cells can then be contractile, but a major limitation here is that there's no bulk organization or alignment of these cells. So this is the general sort of scheme and overview of most of my work in this field. So in almost all cases, I want to take a population of cells. I want to acoustically pattern them. Typically this occurs in suspension. And then I want to do this not in cell media, but I want to do this in a hydrogel precursor. Because we can then, once the pattern is formed, we can trigger the gelation process and use this as a means of encapsulating and immobilizing that pattern cell array. This means that we can then remove the pattern biomaterial from the field, so we don't need to continually apply ultrasound, and then we can carry out a conventional tissue culture or tissue engineering process. So this has to fulfill many criteria. So it needs to be compatible with cell culture apparatus, with conventional cell culture media, and sterile culture conditions. So I've spent a lot of my time over the last 6 years in refining this methodology and equipment. And these are the kind of final designs that I've come up with. So what we have here is we have a piece of acrylic which has been laser cut. And you can see here that these 4 outer cavities, they house these piezo transducers, which when they're wired up to a function generator can supply an acoustic field. So they're set up opposing each other so that they supply an ultrasound standing wave across this central cavity. And this central cavity houses a tissue culture Petri dish, which contains a suspension of cells. So this is a 35mm Petri dish for scale. So this is a real-time video of the acoustic cell patterning process. You can see that it happens en masse, so all of the cells experience this force. They're pushed very rapidly into this nodal plane, and you end up with these very uniform geometric arrays. You can see here that by tuning the frequency, by tuning the different transducer pairs which are on, and by changing things like the phase and the amplitude, you can create all sorts of different patterns. And this is based on my reasonably simple square-based array. And on the very right here in yellow, you can see what we've also got here is dynamic trapping. So we've formed a high frequency cell pattern, and then we've switched the field to a low frequency, and you see this dynamic reconfiguration of the cells from the previous pattern to the new pattern. So it gives a bit more flexibility when it comes to cell-based patterning. So I wanted to see, so what I've shown you previously is carried out in cell media, but what I wanted to really see was whether we could pattern cells within biomaterials. So we explored the use of different biomaterial systems commonly used in tissue engineering. So this includes synthetic PEG hydrogels, natural hydrogels such as agarose or matrigel, fibrinogen, and collagen, and also synthetic or semi-synthetic gels such as GelMap. And the take-home message from this was that there was no polymer-based system which inhibited the patterning process intrinsically. We could form these patterns in all of these different hydrogels. But the one constraint that we really noticed was that viscosity was a major factor. So if we're using very high concentration, very viscous hydrogel precursors, this can dominate over the acoustic radiation force and really restrict or completely inhibit the patterning process. So basically, based on this, we were using towards the lower end of the concentrations of these different hydrogel systems. For example, we used type 1 collagen at 3 mg per mil as an initial look at whether we could use these patterned cell constructs for muscle tissue engineering. So what we did here is we extracted type 1 collagen from rat tail tendons. We reconstituted it in acid as is standard. And then when we were about to carry out the patterning process, we neutralized the collagen solution. We immediately added our cell suspension. We applied the acoustic field. And then we left the whole thing for 30 minutes. So the field was on for 30 minutes and the gelation process was happening over 30 minutes. And this was tuned so that what we would get consistently, we would get the acoustic patterning happening first before the structure formed a gel. So after the 30 minutes, we could take this out and we could pattern the next gel, and etc., etc. So what we saw here was very widespread cell patterning. This is live dead staining on this bottom row. So we can see very healthy cell populations. At day 0, the cells are rounded. This was taken, I think, half an hour after encapsulation. But then we leave these in culture over 4 days. We can see the cells starting to adhere and a little bit of outward spreading towards adjacent fibers, but very generally staying within their acoustically patterned lines. So this was a very nice demonstration that we could get acoustically patterned cells for long time periods. But we couldn't really, in this case, go longer than 4 days. And this was because, I'm sure you'll notice here, we're getting this contraction between the fibers. And this is occurring because the cells are healthy, and the collagen is of quite low weight percentage. So we're getting cell-mediated torsion, which is contracting the gel. And although this could be potentially used as a method for making high-density acoustically patterned arrays, it really prevented any further study of this system, looking into longer-term processes. But what we could do with the collagen system, collagen is very amenable to tensile testing. So we performed tensile testing in two configurations. So one where the load was applied parallel to the fibers, and one where the load was applied orthogonally. And when we measured the tensile Young's modulus, we saw a small but significant increase when it was applied in the parallel direction. So this is nice because it shows that the cellular micropatterning can then lead to bulk tissue properties. I wanted to switch system for the reasons I stated in terms of the cell torsion and the gel contraction. So I looked towards using this gelatin methacrylate or GELMA based system. This is gelatin which has been methacrylated, which allows it to be photo cross-linked to form a covalently cross-linked structure. So this would impart greater stability to the hydrogel and generally prevents these sort of contraction events occurring. So the cell patterning worked fine. And what we can see here is over the course of 7 days now, we can see the retention of the cells within the lines. But we can also see the formation, the hint of these long elongated myotubes, which are formed by the fusion of these individual myoblasts. If we look at these structures at 8 days using immunostaining, what we can see here is something which is starting to resemble the structure of skeletal muscle. So we can see these elongated myotubes, which are then bundled into these acoustically patterned lines. So what we have here is 2 levels of orientation. We've got an individual cell orientation, and we've got a bulk alignment of the cell population. So it's a hierarchical structure that is being formed. So this here for me was a nice demonstration that we can really use this cell patterning to produce a hierarchical tissue engineered structure with a structure that is starting to resemble its native form. But there's a lot of work that needs to be done to modify this system and improve this system, and this is the basis of my ongoing work. So I'm looking at increasing the density of cells within each of these fibers. I'm also looking to, so these are formed in very flat tissue constructs. I'm looking to build more 3D aligned tissue constructs. And then we're also looking to mature these for much longer periods to produce highly contractile tissue constructs. Just want to also highlight that I am not the only person doing this. It's a small field, but there are other people doing some excellent work. So there's been work on patterning neural tissue in vitro using similar methods to mine. There's also been work in forming these endothelial columns, which were then implanted in vivo. And for me, a very interesting avenue for this field of acoustic cell patterning was some work which came out last year by Pierre Fischer at the Max Planck Institute, where he showed that you could use acoustic holograms to encode a particular spatial map of pressure. So you could, in essence, create customized cellular arrays. So moving away from the sort of geometric square-based arrays that I've been working with, here you can just program in a particular geometry, produce the hologram, and then form your acoustically patterned cell assembly. So I think this is a very nice avenue for the future of acoustic cell patterning. And if you're interested in this, you please take a look at these review articles where I touch on these aspects of ultrasound cell patterning, but also other methods for engineering complex tissue structures. But now I want to move on to a slightly different field, and that's the use of ultrasound as a means of triggering membrane disruption. So what's going on here? So membrane-based structures can be disrupted in several different ways. So one of them is through cavitation. So here you have the ultrasound field is stimulating the nucleation and subsequent cavitation of microbubbles. And this cavitation can cause disruption to a membrane if it occurs in close proximity to the structure. You can also get heating-based effect here. So ultrasonic energy can be dissipated into the surrounding media and cause local temperature increases. And then these increases in temperature can cause thermal disruption of membrane-based structures. And then the third aspect here is acoustic streaming. So acoustic fields can produce fluid-based currents. And then these fluid currents can lead to increased number of collisions between membrane structures and increased mechanical disruption of those structures. So all of this disruption has proven to be exceptionally useful for putting material cargo into structures or releasing contents from inside structures. So this is particularly useful in the field of biology and the field of medicine. So we can see here that people have been using ultrasound for bacterial transformation. So introducing genetic material through transient pores formed in the bacterial cell membrane. We can also use it as a method of lysing cells, so removing the cellular contents from a cell and then using these for downstream PCR Western blot analysis. We can also use this in a more synthetic sense, so we can construct synthetic liposomal membranes. We can load these structures using with drugs, and then we can use ultrasound as a means of permeabilizing these liposomes and releasing the free drug. So this offers opportunities here for targeted nanomedicine. So I want to consider this last aspect just in a little bit more detail. So people have shown that through many publications that you can load up and you can controllably release cargo from liposomes using ultrasound. But the cargo which people have always been focusing on is drug molecules. This has been used for nanomedicine. But what I was interested in is whether you could switch out this cargo and instead of encapsulating a drug, whether you could encapsulate another entity and use this again to later on trigger a process. So this led to the hypothesis of maybe we could use ultrasound to activate enzymes. So enzymes are hugely important industrial proteins. So they're used to bind to substrates and reduce the activation energy of key biological processes and then catalyze those reactions. So this schematic which I've shown is a very simple schematic of an enzyme catalysis. What it's not actually showing here is the fact that many enzymes require a cofactor for the catalysis to occur. So this was the rationale here. Could we load up our liposomes with a cofactor, in this case calcium, use ultrasound to permeabilize the liposomal membrane, and then use that cofactor, which has been liberated from the liposome, to activate an enzyme, in this case transglutaminase. So transglutaminase, it requires the binding of calcium to the outside of the protein, to trigger this conformational rearrangement of its tertiary structure into this active form. And this active form can then catalyze an isopeptide bond formation. And we've used this here to catalyze this model reaction between a protein substrate and this fluorescent reporter, so dansyl cadaverin. We've done this because we can then very easily monitor the enzymatic activity using a simple fluorescent readout. So we produced our liposomes, around 150 nanometers in diameter. We loaded them with calcium. We found a hydrating solution of around 400 millimolar was optimum for creating very well loaded liposomes. And we also tested their leakage. So over 120 hours here, you can see that less than 1% of the calcium was released from unexposed liposomes. So these are liposomes which have not been exposed to ultrasound. But when we do expose these liposomes to ultrasound, what we can do here, if you look at the graph on the left, you can see this dose-dependent release of calcium in response to this ultrasound field. So if you look at 50 seconds, with that exposure time, we can release over 90% of the calcium cargo. But if we dial this down to 1, 5, 10, 20 seconds of ultrasound, we can dial down the amount of calcium which is released from the liposomes. And that's nice because it means it's a truly dose-dependent system. And this is reflected in the reaction rate of the transglutaminase. If we vary the ultrasound exposure time from 0 to 10 seconds, we can get a varied reaction rate. So this means that we can now trigger enzyme catalysis when we want, but also to the extent that we want. So we wanted to move beyond this model system of this model protein in dansyl cadaverin and to look at a more natural application of transglutaminase. So transglutaminase, when it's in its active form, is very commonly used as a means of forming isopeptide bonds between soluble fibrinogen molecules and hence forming fibrinogen hydrogels. So this whole scheme really offered the opportunity for ultrasound-triggered enzymatic gelation. So this is the mixture of components after 6 hours with no ultrasound exposure. The rheology is a bit messy here, but it basically shows that we have a liquid retained after those 6 hours. When we apply ultrasound to release the calcium, activate the enzyme, and stimulate that fibrinogen cross-linking process, we see this rapid increase here in the elastic modulus, which far exceeds the viscous modulus. And what we have here is a gelation process occurring, and it's a gelation process that is again dependent on the ultrasound exposure time. So we get a much faster rate when we use 50 seconds exposure than when we use 3 seconds exposure. So this whole process was very exciting for me because it opens up new opportunities for catalysis and gelation. So people have been using the same old triggers over and over again. So light and salt and temperature and pH. This was the first example of an ultrasound triggered enzymatic catalysis. And it's also the first example of an ultrasound triggered enzymatic hydrogelation. So the reason that this is potentially interesting is that ultrasound can be used in ways that those other triggers cannot. So ultrasound can be used to stimulate deep tissue processes because it has a very low scattering through skin. So it potentially offers a route to in vivo gelation. So having said that, many aspects of this scheme, as I'm showing it here, are not suited to in vivo gelation. So The first issue here is the enzyme. So transglutaminase it requires this calcium activation, but the levels of calcium in the body are higher than the threshold for activation of the enzyme. So if we were to inject this formulation, we would get very rapid background catalysis occurring. But the nice thing here is that this system is modular. So what we can do is we can switch out the enzyme, we can switch out the polymer, or we can switch out the cofactor, which gives us great versatility for exploring different enzyme systems or different gelation systems. So that's one thing which we're working on currently. And then the second aspect here is the mode of ultrasound. So I haven't made this completely clear, but in all of this second half of this work, we've used a probe sonicator to deliver the ultrasound field. And this is operating at 20 kilohertz. So this frequency of sound is detrimental to cells, and it's not really clinically used. It's not really clinically used commonly. So we need to also shift away and redesign the system a little bit to make this system compatible with some of the higher frequency focused ultrasound systems that are commonly employed in the clinic. And one way we can do this is by moving away from just having liposomes to having liposome microbubble conjugates. So here we have liposomes which are used as cargo carriers as before, but they're bound to this microbubble, and microbubbles are used clinically as ultrasound imaging contrast agents. What happens here is that they undergo relaxation, they undergo contraction and expansion in an acoustic field, which leads to their cavitation and a quite violent release of cargo from the liposomes. So this is one route that we're exploring because this allows us to access those focused ultrasound systems which are currently used in the clinic. So just in summary, ultrasound can be used as a new trigger for patterning cells, for activating enzyme catalysis, and for triggering hydrogel formation. And I just want to acknowledge the many people involved in this work. Professor Molly Stevens, a fantastic student, Valeria, who carried out the work on enzyme-triggered catalysis and gelation, as well as many other collaborators at Imperial, where I'm carrying out my fellowship. I also want to mention a key collaborator at the University of Bristol, Professor Bruce Drinkwater, who inspired the whole acoustic cell patterning, and I've adopted many of his particle patterning protocols for my own cell patterning work. So also say thank you to the funders, and thank you very much for listening, and I'm happy to answer any questions that you might have. Thank you.
Well, thank you very much, Dr. Armstrong, for this fascinating talk. If you keep, so we have a few questions that came to us. I'll start with my question first, if you don't mind. C2, C12s were my workhorse for my PhD, and differentiating them was kind of like what I did every day. And this is really fascinating stuff, being able to shape how they are dispersed over the plate. And my question is, did you ever try to examine the differentiation speed, the differentiation rate between just unpatterned C2, C12s on a dish versus the C2, C12s that you would have applied your sonication or your sound waves so that you can pattern them closer to the tube formation setup that they were on dishes?
Yes, so not so much on dishes, but in the hydrogels, we compared the patterned C2, C12s to the unpatterned C2C12s, immobilized in both the collagen and the GelMer hydrogels. I didn't look at rate per se, but we looked at the gene expression, and we saw a far enhanced myogenesis in the patterned system. I can't remember the exact time points, but I think this is quite simply attributed to the fact that there's a greater number of cell-cell contacts in the pattern system. You're aggregating these cells together, and as you'll be aware, these cells need to cell-cell contacts to fuse and form those elongated structures. So we didn't look at a rate analysis, but it was clearly beneficial in terms of morphology and also in terms of gene expression.
Yeah, that's exactly what I would have assumed, is that if you pattern them closer to a tube formation structure, that they will in fact then fuse into myofibers and then myotubes at a probably faster rate, whatever that rate is.
Sure.
So we have here a few questions that came along. We'll start with so Dr. Emilio Alarcon asks, what is the impact of the matrix density polymer loading on the sound propagation efficiency, and how would this could affect the resolution of the architectural features?
So that's a very, very good question. So the density will affect the propagation for sure. But we haven't really explored those high density systems, if I'm being completely honest, because before density becomes a problem, viscosity becomes a problem. So as soon as we start getting more and more dense, we start to get viscous impediment of the patterning. I think that's the more dominant factor compared to the density of the polymer. But it's a good question, and it's not something which I've ever sort of decoupled those two effects.
All right. So the next question we have here is from Dr. Ashwani, and the question is, do the parameters of ultrasound changes with the target tissue construct, whether the target is a soft tissue or a hard tissue?
No, I wouldn't say so. The parameters would change depending on, well, for me, the parameters will change depending on the cell structure in the tissue. So you'll notice the structures I was forming for muscle, they were quite thick fibers with with a reasonably wide separation. But if we want to look at patterning structures such as cartilage, which has been another aspect of my work, which I haven't shown, we want to be looking to pattern much finer resolution structures, so almost single lines at much closer spacings. So I'll be adjusting the frequencies to account for that. But because we're starting off with, we generally for all of the tissue engineering I'm carrying out, we're starting with cells and gels, regardless of whether it's a soft or hard tissue. The acoustic properties don't really alter. It's more the subsequent tissue culture conditions which will be varied. And I think I should point out here that because this works so well with hydrogels, it's a little bit better for softer tissues. So for harder tissues where you may want a more polymeric or polymeric mat or a ceramic scaffold to support your growth of, for example, bone, this method is maybe less suited for those very hard tissue structures.
All right. Next question is from Dr. Peter Liu, the Chief Science Officer of the Heart Institute and my boss. How do you keep the patterns of cells and matrix in place once the ultrasound energy is removed in vivo?
So we haven't gone in vivo, but maybe I didn't make it entirely clear. So this is why we're using gels. So we form the arrays within the liquid hydrogel precursor, and then we trigger that gelation process to occur, and this immobilizes the array within the hydrogel, and this allows us to take it out of the field. What happens then is sort of independent of the field. So the cells can migrate out in certain instances, or in the instance I showed you, they were largely retained within their arrays. And I imagine if you go in vivo, there's additional constraints, additional factors here with mechanical forces at play. But no, the retention of the pattern is the inclusion of the biomaterial.
James?
Hi, I'm still here.
It's okay, no worries. And probably Mo is having some issues with the internet. So I'm gonna take over for. We have two more questions. Okay. So we have a question from John, and he say, of course, it's an amazing presentation, and he's asking us from a biological perspective, each type of cells react to different ultrasound intensity in a different way. Even the difference intensity and frequency will be different. For, let's say, it's actually asking if, depending of the type of cells, if the frequency that you will need to actually to produce the effect, it will be actually different. Is that? I think that's the core of the question.
Yeah, so it's a good question. So like I said, the patterning occurs through a mismatch in density and compressibility. Those are the two factors you absolutely need to have. And generally, there are small differences, but generally cells will have a very similar density and a very similar compressibility. So there's no difference there. The other factor is size. So larger cells will experience a greater acoustic radiation force, and that can be used. So people have been using this, for example, for cell sorting. So separating out different populations using very finely controlled ultrasound fields, often in combination with microfluidic devices. So that's a whole field of acoustofluidics, which I haven't really touched on. So as long as if you're getting bigger, you experience a greater radiation force, but as long as you're staying within sort of half a wavelength of the wave that you're applying. So if you start to get bigger than half a wavelength or bigger than a whole wavelength, then you're not going to get any patterning effects occurring, because you can't fit more than one cell into that wavelength, if you get my drift.
Wow. So I have another question from Castro John Bosco. Sorry if I actually trashed your last name. And he's asking, of course, thanking you for your great talk. I'm just saying the same now. He's asking about if the cross-linking methodology of the hydrogel I think it's also that it could be extrapolated to the matrix, really have an impact on the ionic cross, like on the way of the propagation. It's a little bit similar to the question I asked you through Mo, but yeah, that's the question.
Yes, yeah, absolutely. It will do. The property of the material, the cross-linking will change the stiffness, and the stiffness changes will change the acoustic attenuation and the propagation of the wave through the material. But on a practical sense, with the range of concentrations that we're using, like I said, we're using very low concentration solutions. We don't see any effect. And I should also point out here that that we are doing this pre-cross-linking. So the cross-linking will occur after the patterning process.
Okay. And he's actually also has a second part of the question, that if you have tried any other reversible cross-linking methods like ionic cross-linking to pattern cells with the ultrasound. So
ionic cross-linking.
Yeah.
No, we haven't. So I avoid systems where you need to add a second component. So, for example, we take alginate and add calcium chloride. Adding a second component there offers the opportunity to disrupt your patterned array. We could use other calcium release mechanisms to form an ionically cross-linked gel system, and I imagine that would be compatible with the acoustics. I don't see any problem with that happening.
And we keep getting questions, which is a great thing. So Dilip Thomas is asking if the photoacoustic patterning affect the underlying substrate orientation, like in the case of collagen or matrigel, and does the persistence of cell pattern reflect any substrate modification?
So there's a really interesting question. I've always worked on the basis that I mentioned the size dependence of the patterning. So I said if you get larger cells, you'll feel a greater acoustic radiation force. But equally, if you get smaller and smaller, so down to the size of collagen fibrils, these fibers are going to be experiencing very, very weak acoustic radiation forces, which consequently means that they'll be dominated by just simple Brownian motion. So generally, it's kind of accepted that the acoustic patterning is really for these sort of microscale structures rather than the nanoscale polymer components. Having said that, there has been some work by Diane Delecki and Denise Hocking, and they've shown that you can use ultrasound fields to modulate collagen fiber assembly. I think that they postulated here that this was due to thermal mechanisms, so you can get thermal changes which are changing the way that the collagen assembles. But I don't think that there's any sort of acoustic radiation force alignment of the underlying collagen.
Thank you. And we have two more questions. One is from Jean-Philippe. You know that guy really well, Jean-Philippe Saint-Pierre. And he's saying hello, of course, and he's asking you if you could comment on if there is any constraints in terms of the cell patterning in the third dimension, so a little bit of the thickness. So if there is any limitation on, you know, how thick you can pattern the gel, and if, of course, if you're losing resolution as you are actually, the material is getting thicker.
I mean, thank you, JP. So a 3D patterning is something which I've been wrestling with for the last 6 years. It's not easy. In theory, there should be no loss of resolution, but you just need a strong enough radiation force that you can levitate the cells beyond gravity and also beyond any sort of additional viscous effects. So in theory, it should be fine, but practically, I can tell you it's very difficult to achieve well-patterned, acoustically formed arrays in 3D in a biomaterial for tissue engineering. I'll be pleased when I can do that successfully.
It's the next stage for 3D bioprinting with ultrasound.
Sure.
We have another question from Abdulrahman Baki, and is also thanking you for the great presentation. He's asking you if the ultrasound patterning depends on the mechanics, the elasticity, or the shape of the cells, or maybe both, and whether this could be utilized to sort different cell types in solutions, like cell sorting, but using ultrasound. Kind of interesting, actually.
Yeah, and I did allude to this a little bit. So I'll just go back to it is due to the density and the compressibility. And this can be derived from first principles. So those are the two major factors, and size. So if there's differences in any of those three factors, there will be a difference in acoustic radiation force. And you can then start to design devices, for example, where you flow cells through one channel, and then you have a fork, and then you get a different degree of acoustic deflection occurring. So cells which are experiencing a greater radiation force for one reason or another is deflected down one channel, and the other cells go down the other fork. So these kind of devices have been demonstrated. There was one in PNAS, I think 3 or 4 years ago, which was a very nice piece of work. And it is certainly something which people are looking into.
Perfect. That's fantastic. Okay, James. So again, thank you so much for taking the time of doing this with us, and teaching us a lot about this really exciting field that is coming up. I think that it's gonna be the next generation of how we can pattern stuff with structures using ultrasound. It's at the end of the day, it's energy, right? Energy comes in different packages, either photons of waves of energy in your case. And thank you so much. Congratulations for the great job. And everyone, thank you so much. See you next week in another series of seminars. And again, great work. Thank you so much, James.
Thank you very much. Thank you everyone for listening.
Bye-bye. Take care, everyone.
Bye.